Today our topic is coastal protection. The next category of coastal structures that we're going to look at right now is floating structures, specifically floating breakwater. As discussed in wave mechanics, wave energy is concentrated primarily on the upper part of the water column, where the orbital motion of the wave is most pronounced. As a result of that, floating structures can be deployed to effectively reflect and dissipate incident wave energy in order to protect the lee side. This is accomplished through turbulence as well as wave breaking on the structure itself, as shown here in the figures. This figure here shows example of floating breakwater, which typically is put in place in the sea using cables that attach the breakwater and anchor to the seabed. Since floating breakwater is not a massive structure which is constructed on the seabed, it is much less dependent on the bottom soil conditions. This makes it a possible solution to locations where the soil bearing capacity is weak. Besides, floating breakwater is easily adaptable to different water depth and large water level fluctuations because the only component that need to be varied is the cable length rather than the design of the breakwater body itself. This also means that the cost of a floating breakwater is not sensitive to the water depth, unlike a massive structure, because the cost increase in large water depth is only the cost of the cable. Floating breakwater can also be designed to be mobile so that it is only deployed when needed and can be easily relocated. But perhaps the most important advantage of a floating breakwater is that it allows the free passage of current as well as fishes in the gap below, so that it imposes least environmental damage to the local surrounding. Some of the disadvantages of floating breakwater is that it is only applicable to short wave, where the wave energy is concentrated near the surface. For long wave, such as tide or tsunami, where the wave energy occupies the entire water column, it will be able to pass through floating breakwater without being reflected or dissipated. Another problem with floating breakwater is that during storm event, it may be subjected to resonant excitation such that it goes through large motion. Although this may means that the wave can be more effectively dissipated or reflected in the process. However, it is also highly risky that during such excitation, the floating breakwater can be damaged suddenly when the cable snap. This is contrasts to massive coastal structures which is constructed on the sea foundation, whereby their damage is usually not sudden but gradual. This slide here shows example of some simple breakwater, which include prince type, catamaran type, or floating flexible assembly. The plot shows the transmission coefficient of these different types of floating breakwater, whereby the transmission coefficient is plotted as a function of the ratio W over L, W being the dimension of the structure in the direction of the wave, and L is the wavelength. So as we can see here, when the size of the floating breakwater becomes larger, WOL will be large. Whereas if the size is relatively small compared to the wavelength, then WOL will be small. For small WOL value, we notice that the transmission coefficient is high, which means that not much of the energy can be reflected or dissipated. But on the other hand, the energy moves through the breakwater. Essentially, the breakwater becomes transparent to the incoming wave field. However, as the size increases, we can see that, for example, a simple tire assembly for WOL equals to 1, which means that the size of the breakwater is the same as the wavelength, then it is able to reduce the wave energy with a transmission coefficient of approximately 0.6. The effectiveness of a floating breakwater such as this can be tested and verified in the lab environment prior to their deployment on site. Right now, let's look at this simple example. For the catamaran floating breakwater whose transmission characteristics are given on the previous slide, determine the transmission coefficient for incident waves having a period of 2, 4, and 6 seconds. Given the water depth where this breakwater is going to be deployed is 7.6 meter, and the size of the breakwater is 6.4 meter. So we solve this problem by first taking the wave period to derive the deep water wavelength and subsequently the wavelength at this location where water depth D equals to 7.6 meter. Since the breakwater width is 6.4 meter, we can now calculate the ratio WOL for each of the 3 cases, and then from the graph we are able to read the transmission coefficient for these 3 cases. We notice that for a short wave, the transmission coefficient is relatively low, which means that the catamaran is effective. However, for a relatively longer waves, we notice that the transmission coefficient is very close to 1, which means that in this case, the breakwater actually become transparent to the incoming wave. By now, we have completed our study on the design principles of the different types of coastal structures. To summarize, for cylindrical structures where the dimension of the structure is much smaller than the wavelength, Morrison equation can be applied where we evaluate both the drag and also the inertial component of the forces acting on the structures. For large submerged structures where the DOL values are typically high, the use of potential flow model is more common in order to investigate the wave structure interaction. For rigid phase vertical structures, our main concern is the pressure distribution on the C side of the structure, and so from there we are able to determine the net force and moment acting on the structures, and where the pressure distribution is also important on the lee side, then it also needs to be taken into consideration. For more floating type structures, the transmission coefficient is one of the most important design parameter, whereby it needs to be investigated to ensure that the structures are able to function effectively to attenuate the wave energy Also, more footing structures will require detailed investigation into its resonance characteristic to ensure that it does not become vulnerable to sudden damage. For rubber moon type structures, the design is principally um, governed by the type of armor unit and the weight that is required for the given coastal climate, and also the allowable damage that is adopted for the design.